we're on.
All right. So I have got a loop of wire, 3 different loops of wire, different thickness of wires and different numbers of turns. And so I'm going to connect one end of this wire to the other end of this wire. Okay? And I have a magnet here and a galvanometer. Galvanometer, this is the ammeter that goes in both directions.
Microammeter. Ah, I see.
And the units are...
Microamperes?
Yeah, must be. So if I notice that I put the... You show what the magnets are doing. I put them right next to each other.
So when you put the magnet in, it shows that the current is flowing one way, and when you pull it out, it shows that the current flows the other way.
And if I just put the magnet in the middle of the thing, nothing happens. Okay, so, and what happens is, you know what the shape of the magnetic field is like? It goes out like this and loops around. So out here, there's not much magnetic field, and as you go in, it gets more and more intense, right? More and more intense. And then as you pull it out, it's the maximum intensity, and then it goes to less intensity. So what the deuce does that mean? All right, so the magnetic field inside a conducting loop induces a current to flow. And we just saw it's called electromagnetic induction. Here is a magnet north like this going in. And so out here, the field is weak. Remember, Faraday had the intensity of the field was symbolized by how close together the lines are.
Yeah, yeah.
And then as you move it in, the magnetic field becomes more and more intense. All right, that induces a current, which we'll get to more about that later.
And the wire is a coil, is a current.
Yeah, that's a coil of wire.
Yeah.
Or it could be just a metal ring.
Got it.
Same thing. And then here it is going out. And interesting things to notice here is as it goes out, it goes from a strong magnetic field to weaker. Here when it goes from weak to strong, the current goes in one direction. And when it goes from strong to weak, it goes in the other direction, which we saw there. You pull it in, we got the needle going one direction. You pull it out, it goes the other direction. Okay? There's 2 ways that you can do that. You can either move the magnetic field or change the area of the loop. Now, what the deuce does that mean? If I have a loop like this with a magnetic field,
We're good.
the magnetic field, I get one thing, okay? But what happens to the magnetic field inside the loop if I turn it like this? Here I've got the maximum amount of field. Here I've got the minimum amount of field. If you think of the field as those lines, more lines, fewer lines. So there's 2 ways to do that. You can move the magnetic field, or you can do this, or I can't do this, I need another hand. You can go like this.
Yeah, okay, yeah, both those options.
You could also do that, and that would change it. So all of those will induce a current to flow.
Magnetic flux.
Magnetic flux. Flux comes from the term flow, is the amount of magnetic field passing through an area perpendicular to the area. Okay, the symbol for the magnetic flux is the Greek letter phi. Phi, like phi. All right, so here's a very poor copy, but here the angle of the area is normal to the surface. It's going to be normal. I'm not going to do. It's just normal to the surface. And here we've got the magnetic field is perpendicular to the area. So here you have all of the flux is the amount of field flowing through this area. If you turn that 90 degrees,
now you've got
nothing. Now the normal is perpendicular. Now there's no current, I beg your pardon, there's no magnetic field inside that area.
Yeah.
And as you turn that, it was the same thing I was doing
a little
minute ago.
less.
As you turn that, as you go from perpendicular like this, which is maximum, to this, 0, you get different amounts of flux. And flux is just the flow, means flow. It's how many lines of magnetic force pass through the surface. All right?
Cool.
All right. So
Badass.
here's the badass. I like that. It's a badass thing. It makes electricity. So that's the intensity of the magnetic field times the area is equal to magnetic flux. So let's say that everything's perpendicular. If you have a larger area, you're going to get more lines through that. As the area gets smaller, you're going to get less and less lines.
That makes sense.
And this phi, we had theta before. This is a different one, but it means the same thing. It's the angle between the magnetic field and the normal. Theta would be the angle between the magnetic field and the surface.
Yeah.
So phi is between the surface and the normal. Okay?
Great.
So let's put that over there.
Let's add that bad boy.
So that's
Cosine
I
phi.
missed it. All right, so the units of magnetic
Weber.
field are the units of magnetic, I beg your pardon, magnetic flux is the units of magnetic field, Teslas times area. That's Teslas per square meter. How many Teslas of magnetic field for every square meter?
A Weber.
And that's a Weber.
I have not used that in a sentence ever.
Yeah, and you know, the thing is, we're not going to really, I should keep my mouth shut here. This is page 701. Now the hell with it. Click. Oh, I moved it. Dog lips.
Having
Okay,
two
there it
screens.
is.
Okay.
Okay, here's Faraday's law. And basically it explains what we saw over there with the loop of wire and the bar magnet. Changing the magnetic flux in a conducting loop produces an electromotive force, EMF. And EMF is what a battery produces.
That's what we saw over here. What do we call it? The motor
The motor, well,
effect?
actually, if you have a battery, there's an internal resistance. And then there's the electromotive force.
Gotcha. Okay.
So this electromotive force is provided by a battery. What is that? Electromotive. What does motive mean?
Motivation.
Yeah, motivation, motion, movement.
Yeah.
So moving electric charge. So changing the flux inside produces an electromagnetic force. Okay, and magnetic flux can be changed by 3 ways. You can make more magnetism or less magnetism. That's like on that device over there where you've got the coils. You can change the magnetic field by changing the current flowing through it. You can change the area, which is what we're doing with this thing here. Or you can change the angle, and that's just like that. Okay? And all of those will produce a change in magnetic flux. Motional EMF. Not emotional, but motional EMF.
So the E with the fancy E,
It's a Greek letter.
it's electromotive force.
Electromotive force. It's the force that makes the electrons move. Where's the Greek letters? Yeah, it's epsilon.
Epsilon.
Okay, so that's the change in the magnetic flux. It's a rate. It's the rate at which that it's changing. And we could see that when I was moving the bar magnet. If I move it very slowly,
Not as much.
Not much. If I move it fast, I get more. Now, why is that? You get the same change in flux, but it happens in a smaller or larger time interval. And if the time is shorter, you have a larger electromotive force. Now, that was measuring current. And what is required to make current flow? You have to have a voltage. You have to have an electromotive force to make it go through the resistance.
So the electromotive force is the volt.
The units are volts.
Yeah. Okay.
Batteries also have electromotive forces.
Yeah.
It's produced by chemical reactions.
Okay. The electromotive force.
Okay, you can change the magnetic force by changing the area, by changing the magnetic field, or by changing the angle. So you've got this.
Okay, I see it.
Equals delta A B cosine phi over time. Okay, and rather than do all three of those, all you got to do is change one of them over a time interval.
Gotcha. Okay.
There are two things going on. Life is never easy. Okay? So we've got a magnetic field that induces a current. So a current flows in a wire. What appears around the wire when a current flows?
The magnetic field.
Yes.
Yeah.
Things are getting more complicated.
Yeah.
So what happens is the change in flux produces a current, and then the current produces
The
magnetic field due to the current. Current.
Yep, I remember you doing that before.
Okay, so, and we'll use that to tell the difference between what is what. Also, Faraday's law, so here it is before for one loop. Here it is for a number of loops. So let's take a look over here.
You know, like how many loops?
Here, this has, it probably says, but I can't read that. It has a, okay, now let's do this one.
Barely anything.
Hardly anything. Now let's do this.
Looks like thicker.
Yeah, this is thicker. So one loop, hardly anything. And this, there's more loops than this, but this has the maximum number of loops.
I see.
You can see how thick this wire is.
Yeah.
And how thin this wire is. So it's not the thickness or the thinness of the wire, it's the number of loops. Here, this is B equals delta phi over T. This is where N is equal to 1. Here, B is equal to delta phi over T times however many loops there are there. And I believe that's printed in there, but I can't read it.
Let me see. It says.
Oh, this says one turn.
It says 100, and then.
100, one turn.
I think this one says 25.
25. So what those in the number of turns. So, and you can see right there, we had the same area. We had the same amount of flux. The thing that was changing there was the number of turns. All right.
Is that a negative sign in front of the N?
The negative sign means that the current produced by the
electromagnetic
by the electromotive force
motive force
produces an induced magnetic field that resists the changing
flux. This is the lenses law you're talking about.
Okay, now what this is how can you predict which way the current is going to flow?
Yeah.
Okay, let's go back to here.
That was my question. I was like, how do you know which way it's going to go?
Yeah. Here, as you go from the splayed like this to in here, the B is increasing. So as the B increases, the current goes this way.
Counterclockwise? Or?
Well, you can see it goes like this.
Okay, yeah.
All right, well, check it out. what direction is my thumb pointing?
To the left.
To the left. So what happens is you're getting more field in this direction. It makes a magnetic field that tries to oppose that. It's like politics. Whatever party's in office, the other party opposes everything they try to do. So think of it as that. Think of it as politics. This is increasing the field. It generates a magnetic force, a magnetic field that tries to cancel the other one out.
Got it. Okay.
Okay. And now what happens here? Now it's pulling out and going from more B to less B.
Yeah.
Now the field is this way. See how it's going this way? Now it's trying to make more field. Whatever it's trying to do, it fights it. So it's trying to make less field. The bar magnet's making less field. It generates a magnetic field that tries to add to it.
Okay.
Isn't that wild?
It is wild.
This is Lenz's law.
And that is how we have that negative. Okay.
That's why the negative is there. The electromotive force that's generated resists the change in flux. So let's read this again. The negative sign means a current induced by the electromotive force produces a magnetic field that resists the changing
Flux.
So if the flux is increasing, it'll try to decrease it by going the other way. If flux is decreasing, it'll try to increase it by going the same way. Yeah, politics. I hate politics. So here's an example. Here the B field is increasing. Okay, and so the flux is increased. You got increasing magnetic field, and the field is this way. So if the field is increasing, it's going to make inside the loop, it's going to make a magnetic field in the opposite direction.
Okay, I see that.
Okay, so I'm going to do this over here because it won't break my arm. It's going to make, if the field is this way, it's going to make a field in the other direction, which will make the current flow around like this, right? And over here, the field is trying to make more, and so it contributes the same. And so what happens here, now the magnetic field is going out, the field inside is decreasing. No, don't change, don't change. And so now, since it's decreasing, the field is here, it's less and less and less of this, it makes a magnetic field inside that wants to increase the field. So inside, that means the current is going to flow in the other direction. And it wants to increase the flow.
Yeah, that was right, I think.
It wants to increase the field.
Yeah.
It wants to flow in this direction, that direction around the loop.
Yeah. And we know that the B is going in because it tells us here, right?
Yeah.
Like, that's why we know that. Okay.
All right, so understand that so far?
I think, I think I got that.
Kind of makes sense. Lenz's law is used to predict the direction of an induced current. That's what we just did. We just talked about Lenz's law by example. Here it is. A changing flux induces a current whose direction of the induced magnetic field opposes the change. If the magnetic field inside is increasing, it opposes that. It tries to decreasing by putting magnetic field in the opposite direction. If the magnetic field inside is decreasing, it fights that by putting a magnetic field in the same direction as the outside field. Increasing flux produces a magnetic field. That's what I just got through saying.
Yeah.
And decreasing flux produces a magnetic field in the same direction. And you use the hand rules to determine the direction of the induced current. All right? Now, I want to show you something. I hope I can find it.
That was easy.
here is a copper tube. Come on. There you go. It has two things in it. One is a magnet, one is not. Okay, one is a magnet, one is not. And what you can think of, this copper tube, is a series of circles. Okay. And I don't know which one is the... All right. So if I drop this through the tube...
Oh.
Notice they put the little rubber thing in. It drops right through. All right, if I drop this one through...
Much slower.
And why is that?
Because the electric fields are interacting with each other? Or something, right?
Because
like
it's generating
an opposing...
What happens is this generates a current in here. And that current produces a magnetic force in the opposite direction. So this is a magnet, and so the magnetic force generated by the current in this, which is going around in a circle, fights this.
And slows it down, pulling it up. Yeah.
Yeah, and it's really cool to look at the difference between this one. I can barely get my hand down there fast enough. And this one.
Cool. That's cool.
So that's Lenz's law.
Okay.
All right.
I feel like I need some like practice on like how to like look at those and like actually answer a question, but I feel like I understand it in theory. Oh great, a practice question. Okay, where do we start? Number 3, number 2?
This one, not this one.
Okay.
So you got a square loop. What does it say?
A square loop of wire of size 0.2 meters has a total resistance of 0.6 ohms. The loop is positioned in a uniform magnetic field B of 0.030 Teslas.
Yeah, hang on. 0.30?
0.030.
0.030 Tesla. All right.
Okay, the field is directed into the page perpendicular to the plane of the loop as shown as above. Okay, so calculate the magnetic flux through the loop. So our flux is badass.
So
Sorry,
I really like it. So this is equal to 0.030 Teslas times
the area
0.2 meters squared.
Yeah, and then do we have to? Oh no, it's the cosine of
Well, it's
90,
everything's
so
perpendicular,
it's
so we're going to ignore that.
We're good.
0.030 times 0.2 squared, so that's 0.0012 Webers.
WB. Okay. Now calculate the electromotive force induced in the loop during this period. So our electromotive force is the change in the flux over time. Oh, sorry.
Oh, the field strength increases.
I didn't see that there. Sorry. The field strength now. Oh, and that's to help us with letter B, right?
Okay, so this is B1, and B2 is how much? 0.020?
0.20.
0.20 Tesla.
In 0.5 seconds.
Time is.
So there's a change there.
Seconds. So, and they're asking for the change in the flux.
Calculate the electromotive force induced in the loop during this period. So yes, so we would do.
All right, the electromotive force, everything's perpendicular, so I'm going to ignore this because the cosine of 90 is 1.
Mm-hmm.
Okay, so it's going to be.
Well, can't you just do the change in? Can't you just do this one minus this one over the time?
Well, the change in flux, I'm going to have to. Well, here's what I'm going to do. I'm going to do area, which is 0.2 meters squared, times the final 0.20 Teslas minus the original 0.030 Teslas. See, because it's the change, and what's changing about the flux It's not the area.
Okay.
It's the intensity of the field. And we got how much? Half a second?
0.5 seconds. So you can't just say the change in this divided by time.
Well, yes, you can, but the question is, what is this? It's the area times the magnetic field. So they want the electromotive force?
Calculate the electromotive force, yeah.
All right. So in order to calculate the change in the flux is how much magnetic field is going through how much area. The area is not changing.
I see.
The area is not changing. That's the area.
Oh, my bad. I was thinking this was the B. I was forgetting that's not flux.
Well, this
is not
was the
B.
first one.
Yeah.
And this is the second.
I see. Okay.
It's all good.
Yeah.
All right. So we got 0.2 times parentheses 0.2 minus 0.03 divided by 0.5. I get 0.068 volts.
Okay.
So the electromotive force is 0.068 volts. 0.068. Hello. Volts. I bet they're going to want what the current is next.
Okay, calculate the magnitude of the I of the current in the loop during this period. And then also wants to know the direction and to
And what I'm
justify.
going to do is I'm going to use electromotive force over the resistance. That's
I see.
0.068 volts divided by 0.6 ohms. That's going to be about 0.1 something. 6 ohms.
That's cheap. No, I'm just kidding.
No, I do have it there.
Yeah.
Divided by 0.6, 0.11.
Okay, so 0.11 amps. Right? Okay. And then it says, what is the direction of the current? And then justify. So.
Okay, so what determines the current? What determines the electromotive force? Now, isn't there supposed to be a negative in front of this?
Is that the one? Yeah.
I think there's supposed to be a negative in front of this, so that indicates that the electromotive force is going to resist the change in the flux. Is the flux inside going up or down?
Hold on, I'm not sure.
It starts off at 0.030.
Okay.
And then in
it
half a second it
increases.
goes to 0.20.
So it's increasing.
So that means that the BI wants to decrease.
Okay, because the flux is increasing, so that the electric field is going to be decreasing.
It's going to fight it. So
Yeah.
if this is in, it's going to want to come out. That means it's going to make dot X, dot X, dot X. Because inside, it's going to try to cancel by making a field that goes this way.
Yeah, okay, so, but how do you know what the direction of the
Okay, the field comes in from the bottom, up in the back, towards you on the
see.
front. Your
Okay.
fingers only curve in one direction, and the thumb goes that way.
how do you know which direction the thumb goes there?
It's attached to your hand.
Oh, okay, got it, duh, okay, duh, you can't
So
go
there,
like that.
remember, if you have a straight wire, there's something that's going straight, and there's something that's going around in circles. The straight wire is straight, and the magnetic field goes around in circles. It's going to go up one side and down the other, depending on the direction of the current.
Got it.
So I don't know the direction of the current, but I
you
know
know?
that Lynn says that the current is going, that's what this negative's about, is going to resist the change. And since it's going from 0.03 to 0.2, it's increasing on the inside, it's going to try to decrease that. So what this is, that's magnetic field coming out. All right. So the magnetic field coming out means the current is going that way.
Okay, and then we knew that, like, why did you put that arrow right there?
Well, it's the current. That's I.
Yeah. Oh, I see. And with this, got it. Okay.
I could make it here.
I got it. Yeah. I thought I couldn't remember when you wrote that. So okay, that makes sense.
Yeah, I did that kind of fast, and that's my bad.
Okay, so yeah, that makes sense. So the flux is increasing because it's going here, and then it's
so that means
increasing.
that the induced magnetic field is going to try to decrease it. It's going to fight it. Whatever this says, I'm against it.
Yeah.
Have you ever known anybody like that?
Yeah.
Yeah, I was DTA president, and
and then the current is going to be counterclockwise, right?
counterclockwise.
Yeah. And then to justify, we talk about what we just did.
Well, and you just say it, okay? The field inside is increasing. it'll induce a magnetic field that fights that. So it's increasing
Lenz's law.
going in. It'll try to decrease that by making magnetic field out.
Resist it. Lenz's law tells us it resists.
Yep.
Okay. And then lastly, describe a method by which you could induce a current in the loop if the magnetic field remained constant. So the only way that you can induce something is if you
Change the area, change the magnetic field, or change the angle.
Yeah.
So can we change the area here?
Well, and the time too, right? Right, because how fast.
Well, yeah, well, that's true. Those are all variables.
So you could choose any of those and talk about them.
Yeah, you could change the time it takes to change. You could address this. You could change the time it takes to do this. You could change the area. Although how would you do that if it's a fixed piece of wire?
So what you really need to do then is change the angle
You
here.
can change the angle.
Yeah, because if you can't change anything else, everything's set in stone. That's the only thing that you can change. So okay.
I just noticed Slayer. Is that? Did I have to give that to you?
No, I got this.
All right.
My pajama shirt. Okay, cool. Nailed it. We good?